In Genesis Bible, they said, God said, let there be light, and there was light. And similarly, on August 2011, God of Silicon Valley said, the software is going to eat the world. And so started software, right? People forgot about hardware. And most companies, the largest hotel company is a software company. Largest taxi company is a software company. So that's, I had an opportunity to meet the CEO of BMW. He said, we are a software company that happens to be in the business of some automotives, minor details. Now, I was thinking nobody will come because it's a hardware session. And the other day, my son asked me, Dad, why did they call it hardware? Is it because hard to find, hard to get funding kind of problem? That's why you call hardware. So, however, lately, I think that there is a huge resurgence in the funding of hardware. So, first of all, robotics, AI. I think all these companies that are darling of Silicon Valley and the world, like the Amazon, Facebook, Google, are spending enormous amount of money in developing hardware. So we have created this session, is hardware going to now start eating the world? And I have requested Vipin, Dr. Vipin Chaudhary. He is a professor at UC, he is a professor at SUNY, State University of New York at Buffalo, and he has been loaned to United States government to head up to be the program director at National Science Foundation, NSF. Vipin has done some startups, Scalable Informatics, a storage company. Vipin also did some other startups, and he was also CEO of a HPC cloud company called Tata Sierra, and that was acquired by TCS. So with that, I'd like to introduce, I'd like to invite Vipin. He's from IIT Kharagpur, and he will introduce the other panel members who have spent lots of time in the hardware industry. Thank you, Vipin.
Thank you, Ashish. Well, welcome to this exciting panel. Very pleased to have three very eminent hardware folks here. Let me start by introducing them. So on my immediate right is Debajyoti Pal. He is currently the chief scientist at Cadence Machine Learning. He's also a fellow of IEEE. Previously, he's been the VP of technology at Qualcomm. He's been CTO of Tallwood Ventures Capitals, CTO of Iconos Communication, and he started his career at Intel and Bell Labs. He is from Kharagpur, 1980, moved on to Stanford for his PhD, and he's also founded Excess Bandwidth, which was acquired by Virata. So welcome. And next to him is Nisha. And Nisha is the co-founder and CTO and VP of research at Parallel M. And she's focused on production machine learning. She was fellow at SanDisk and Fusion.io with deep expertise in storage, NVMs, and those kind of things. She has worked at Intel, Gear 6, Sun, and she has 54 patents. And she's a graduate. She got her PhD from UC Berkeley. Welcome, Nisha. And then we have Ashish on the far right. Ashish has been at NVIDIA for 15 years. He currently runs the SoC operations at NVIDIA, which includes Tegra and autonomous vehicles and all of those. He's a 95 IIT Kanpur graduate, and then he moved on to Minnesota to get his master's. Previously, he's worked at Intel and a couple of startups. So welcome all. And if we can very quickly start the presentation. Software is eating, oh, sorry. That's old news, right? It's now hardware is eating the world. So those are the three I introduced, Ashish, Nisha, and Debajyoti Pal. So if you look at our daily life today, I mean, it's made very simple because of the voice recognition in smartphones, the easy commerce we have. I don't see that there, actually. Yeah. The voice recognition and easy commerce, if you look at Amazon, the auto response to emails, very accurate weather response, autonomous vehicles, smart robots, home automation, medical diagnoses, personalized medicine, defense and security, and even enabling science. So if you look at the latest science things that happen, discovery of new particles, gravitational waves, new galaxies, synthetic biology, all of these are enabled by deep learning and machine learning. That's really disrupting everything in our lives, including science. So, and what we are saying here as a panel is this disruption is possible only due to hardware. I mean, you might ask, really? Hardware? Well, if you look at Moore's law as applied to single thread performance, that's gone up only 5 to 10% a year, right? And the power constraints are a lot worse now. So, but yeah, it is really hardware. Look at the many core processors like the GPUs and the TPUs and so on. There, the performance increase has been 5x every 2 years. And for deep learning type, it is that every year. Forget 2 years, right? FPGAs are also chiming in. So data explosion has also helped. Now, the data that is coming is also coming from hardware. It's from IoT devices, machine-generated data. It's not what me, you, and others are generating. So the data is mostly from hardware. So I would say that hardware and data have enabled this deep learning, machine learning. Well, I would be kind of lying a bit if I didn't say software played a role. So hardware, data, and software, and mostly open source software kind of stuff, has enabled this. So now, a lot of the problems that were very hard to solve previously are now being solved, right? And the way we are solving them is we are using a lot of data to train. We are using a lot of hardware to train. And where does the software fit in? Well, you don't have to spend months of engineering effort now to actually fine-tune your software. Rather, you just have to train the network on that hardware with enough data. So if you look at what's going to happen, is that because of this explosion in deep learning and machine learning, more and more dedicated hardware is going to come in. They're going to be specialized hardware for specific problems, because the problems that are being solved by this are economically viable sizes. And with that, I would like to start with some questions for the panel. And so the first question I had was, how is the software model changing? And we've sort of shunted out software. Will hardware write software someday? And will hardware create new hardware? So one of you wants to take that?
Sure. I mean, I think what we are seeing on the software model is all the algorithms people used to use in the past in computer vision, speech, even on the graphics side we see, where a lot of algorithms and a lot of specialized hardware and software was being developed a lot, and with many years of expertise and many years of software development has now changed into essentially trained networks. And you have enough data and you just train the networks, and now you are able to gain all the many gains what we are seeing on computer vision side has been many-fold in accuracy of detections. Same thing on the speech side, and same thing even on the graphics, and as you said, even on the medical side and even in the basic sciences. So I think what's happening, the way, fundamental way of how software used to be written with deep expertise on software side and many layers of software model is going to change more into train the network. You have the data, get the data, train the network, and then you have your software arriving at. So at some day you could assume that some of the basic pieces of software, maybe you can train a network to write a software and create a software out of it. So that may happen someday.
Yes. So kind of to add to that, I mean, so in the research community of software, is some early evidence of this fact. So you can basically see that very classic software structures like B trees and search indexes, for example, people are showing that those can be replaced by training a machine learning algorithm to, and can be replaced by a neural network. It's very early in that area, but there is early evidence that that is possible. That coupled with the fact that the software APIs actually are abstracting very, very heavily. And that enables, the insertion of hardware and the greater functionality of hardware underneath without too much impact to the developer, because the APIs are abstracting, and rather than saying, like 10, 20 years ago, if you want to write a machine learning algorithm, you wrote it in C, and you wrote it, and you knew everything. You managed everything. Now you call an API. And what happens under that API, you don't know, you don't care. So, and that enables a great deal of hardware innovation.
Okay. So let me start with the next question. So given that the power consumption, the footprint, the storage, the memory bandwidth are very difficult issues, what are the considerations for the deep learning, machine learning hardware that will be on the edge? And how is that different from data center or enterprise?
All right, so I'll start with that question. Essentially, machine learning so far has been happening largely on the cloud, and there has not been really a lot of constraint that has been put on how much compute power is needed. Compute power is made available as required, as needed, by having a server farm with lots of CPUs and GPUs and et cetera, infinite amount of storage and what have you. And typically, to train a complex network, it also requires huge amounts of data, and could take days, could take weeks, depending on the size of the network, depending on how many parameters are being trained, and what kind of data, how large is the training data set, and how many times you have to sort of go through that. In machine learning terms, these are called epochs or whatever, so how many epochs you need to actually converge. But once a network is trained, typically what we are seeing is that the use of that network, so network is trained to do what is called inference. And these inference engines have been also put on the cloud, but slowly they are finding their way into edge, where these trained networks are being put on the edge. It could be a car, it could be a gateway, it could be even a phone or a camera, or even could be an unmanned vehicle, which needs to make intelligent decisions and provide results based on the data that comes into it. And that's where the challenge lies in: how do you actually do that computation on that edge device? How do you store the data? If you can't store the data, how do you read this data in and out? And what footprint even is reasonable for those devices? So there is a huge difference in terms of the requirements for edge, depending on whether the edge is, again, the edge is a car, is it a handheld battery-operated device, is it something in between? And the power profile of that, because even though, sometimes you might say, oh, it only consumes a few watts, it may not be reasonable for a phone. It may be reasonable for another device, et cetera. So I think it's a challenging problem today to be able to put this on the edge devices because the requirements for storage, requirements for computation is very large. But from my perspective, I think there's a lot of work to be done in order to create networks that can be reasonably put on those devices. How you compress or other techniques to reduce the storage or footprint, and how do you reduce power consumption?
How do you take the data from these individual distributed edge devices and learn from that? And does it go back to the cloud for the learning and then get pushed back? The inference gets pushed back?
Typically, the cloud is basically creating the model by collecting data, but unfortunately, it's a general model for all the devices. It's a broadcast. There's no localization. I expect the localization will come over time. There will be fine-tuning and localized learning, but it's not there today. Today is simply that of how to take a model from the cloud or cloud pushing a model into the device, how to simply even just accommodate that on that device and do the computation and accommodate the storage.
So I definitely agree. So the stage of edge, I think, it's still very nascent. And until very recently, there was really very little machine learning of any kind on the edge, and the challenges were more on authentication and security and just the sheer difficulty of deployment. There are, from a machine learning perspective, inference is clearly the first one that goes there. And even inference, depending on what it is, it has different challenges when you have something that's something like an industrial IoT kind of device that's spewing multiple variables, very, very fast and has very, very quick turn times to detect faults. The compute is very intensive. And sometimes what's on the edge is a full-blown Xeon multi-core device with as much as a terabyte of storage, which you don't think of typically as edge, but that is edge. So in the machine learning theoretical space, there are techniques that could sometime in the future be applied. I don't think they're practically there right now. So one of the most intriguing ones is something called federated learning from Google, where the basic idea is all the edge devices learn with their local data, and they swap and combine learnings. And this has many benefits in that data doesn't move, privacy is preserved. And so there's stuff waiting to come out, but the edge isn't ready for that yet, and it's not out there yet.
Okay.
Yeah, I agree. I think the main thing on the edge is power is an issue, and you will do the inference on the edge where the latency and the real-time nature will be important, and also the bandwidth. So if you are doing an inferencing on a device where the bandwidth is like Google Voice or Alexa are an example where all the inferencing is done in the cloud, the real-time nature is not as important. You can send to the cloud and get the data. But if you're trying to do inference on a car, self-driving car, where the real-time nature and the amount of data you are collecting is both critical and you cannot send it to the cloud, I think the inferencing has to be done on the edge. So I think that variation, that will determine where you're going to do the edge. Plus, at the same time, also, you cannot do an inferencing sometimes on just one camera, because to make a sense of what's happening around you, you have to look at all the other sensors and all various other camera feeds. So that would also determine whether your inferencing is happening on that camera versus happening, some people call it a fog or some other device, which will be much bigger device. So I think it will vary based on that, and different solutions will emerge based on the needs.
Okay.
Just one more comment.
Yeah.
So essentially, I think there are factors that drive the need to do it on the edge, as you mentioned, along your lines: privacy,
Yep.
latency, connectivity.
Yep.
And these three things have to be there. So for some reason, for example, a friend of mine runs a company that builds baby monitors, and they send images continuously, and that gets stored somewhere in the cloud. You may not want that. You may not want all your security camera at home to be sending all the images and be stored in the cloud. So you only want to send the alerts. So there are these sensitive applications where you want it to be done on the edge. Recently, I think, Alexa recorded some message and forwarded it to somebody whose number was there in the contact list. So, I mean, that's just an example of malfunction, but I'm just saying that more and more, sensitive and private nature or latency sensitive, like where the action has to be taken right away. And if the connectivity is not there, for example, a drone cannot be, for example, waiting for results from cloud to tell it to go this or that, or it needs to decide right on there, otherwise it will hit something. Those things will have to be on the edge.
So it's likely that you will have custom hardware for the edges. I mean, something which is very low power, the neuromorphic type processors coming in. So looking at the custom hardware for these key applications and the distribution of compute to edges, what is the future of classical general purpose CPUs? Are they going to exist?
You mean for the edge or for?
Overall, for this kind of domain?
Also, today, if you look at it, GPUs are used largely, 90% of training in data center is GPU, and 90% of inference is basically on Intel CPU. That's sort of like the breakdown. Although, I mean, it's maybe there.
But looking forward, if the edge requirement is low power.
Yeah, so on the edge, so today, if it is you need to just do a still image face recognition, maybe you can do it on ARM CPU because there's no time sensitivity. But if there is more computation that needs to be done, there is some speed of response, and depending on how much it has to be done, it might require more computation, and that might require customized hardware. And on the edge, depending on application or vertical, I think there will be differences. The speech processing kind of edge device may have a different kind of hardware processing versus if it's vision. They could coexist. Right. But you could customize based on need. And the other thing that might happen is I'm seeing some resurgence of analog computation for power reduction, which is another thing that probably is not done in a CPU or GPU today, but those kind of stuff might come in the edge.
So yeah, so the question primarily is what is the future of general purpose CPUs
So
in
that
this
maybe
domain?
I think.
Yeah, so I think what we see is, particularly on our SoCs we build, we have every combination. We believe that there is a need of CPU for doing single-threaded performance. There will always be application, some decision-making needs to happen, which will require a single-threaded, where there is a more branching kind of applications. On the inference side, we don't do as much on CPU, rather it's much more on GPU, and we have, for algorithms which the problems has been solved, you can make a custom purpose build. We have made accelerators as well. So I can see that also will happen. And in some cases where you have a very so we see a whole range of CPU and GPU and accelerators will coexist. And it depends on where you are in the spectrum of things. If you are only doing a particular CNN acceleration, only thing you do is image recognition, and you know exactly what network you are build, everything, then you build a custom deep learning accelerator. But if you are, I mean, the thing with the accelerator and the hardware is it takes 3 years from we start to design today to go to production. It's a 3-year cycle. It's not a 6-month cycle. So the algorithms which we know today will get productized in 3 years. So if you know everything about that, that's exactly you're sure you're going to deploy that, then accelerator will make sense. But other than that, the GPU will still, I think, bridge that gap for a long time. And then the CPU for really special purpose, single-threaded performance where it matters, CPU will exist. So I think all the CPU, GPU, and accelerators will coexist. And it depends on what applications you are targeting. If it is really targeting a smart camera sensor, then maybe you will have more accelerator, less CPU. If it's targeting more autonomous vehicle application, then all combinations is needed. So that's how I see.
Yeah, so I think maybe just to add to that, I think at a high level, I would agree that there's kind of a role for all things. I think what's happened with the general purpose processor is that the ability to, accelerate on all metrics, is just no longer possible. You cannot accelerate on single thread and multi-core and keep the memory bandwidth and keep the memory latency and keep the memory capacity growing all at the same time. And the fact that, problems are emerging that are very well structured. So the ML problems are extremely well structured in their computation. And so it's always the case that when a problem is well structured and there's an enormous volume of it, custom hardware will be able to do it. That doesn't mean that the breadth of problems does not exist. And the breadth of problems is what the general purpose CPU handles well. And so that creates a position for both. And then anytime there's a unique power constraint and a cost constraint, that also creates the opportunity for special purpose hardware. So there's a need for having all. Another trend, perhaps by what understanding, is the intersection between this and the cloud world. Because one of the biggest things that had happened in the past was that you had a need to waterfall. So when you bought a piece of hardware, you had to use it over its life for more than one thing. And that forced you to buy general purpose hardware, whereas now if you're just going to the cloud, and it's the cloud vendor's problem, how much to provision, then suddenly, and if the cloud vendor has enough customers at any time to justify the life of the general purpose hardware, now suddenly life is good for the general purpose hardware.
Right, so one other comment, two comments, one for the data center and one for the edge. On the edge, the other thing that exists today is the DSPs. They are in basically pretty much all embedded devices. Typically, the CPUs are in the control plane, DSPs are in the data plane. Some of them have GPUs as well. So I wanted to mention that because every phone, every camera, things of that nature, or even smart speakers, they all have DSPs. And DSPs are also adding machine learning AI capabilities. And that's growing. On the custom hardware side, if you look at the prime example is a TPU. It's not a GPU, it's not a CPU. And to Nisha's point, they kind of went and looked at what are the most commonly used operations in machine learning training or inference algorithms and built hardware to accelerate the most used computations like matrix multiplication, some activations, how to pattern the data preparation for feeding into the matrix multiplication for doing convolutions, et cetera. They did all these things. But so that's another angle that is also going to stay, and it will just probably cover over time more and more operations. But if there is something that's not covered in that, it will have to be handled by the GPU or CPU because that will always be there.
Okay. So next one is two-part question. Are TPUs going to replace GPUs? And how will the hardware or system on chip look in future?
So I think it's a continuation of the same discussion. As I said, it takes 3 years for designs to start today and coming out to production. So for algorithms which you know exactly what it is, if you've structured it really well, you can design it, great. I mean, accelerators, TPU is kind of an accelerator in that regard, will exist. So I believe both coexist, and for a long time, because the AI is just really starting, right? We are seeing the whole explosion of research. The algorithms which are today were not there 3 years ago. 3 years ago were more all really focused on CNNs. Today it's more reinforcement learning. New approaches are coming, and the hardware was designed 3 years ago cannot address today's needs. So even if you look at in the Google Cloud, even though they have TPU, they also offer GPU. So both will coexist, and we believe in terms of the innovation constantly happening even on the GPU side. So we don't see them as either or. I think it's a much more they are together and they will coexist. And I think this space is going to be so vast and so expanding that there will be scope for every piece of hardware. And that's kind of second thing is looking into what SoC will look in future as how we build our SoCs today, what we are building in future is always we'll have components for everything. We'll have a CPU, we'll have a GPU, we'll have an accelerator, and some algorithms will still need the traditional DSPs. So you will have some component of that, I think. But more, we will see less becoming on CPU and less on DSP and much more happening on the GPU and the acceleration part of it. So I see the trend moving in that direction versus what it was 5 years ago.
Okay. So the memory hierarchy is seeing a lot of changes, right, with the advent of all kinds of new technologies. how does this intersect with the ML trend, where most of the algorithms, they work in memory?
Right, so I can start off that one. So, I mean, so the memory hierarchy has been kind of seeing the same, at a very, very superficial level, the same kinds of issues as the CPU in terms of you can't be better in all things at the same time any longer, and so you need to kind of bifurcate. The new memory technologies that are in the class of 3D XPoint, which was announced by Intel, many companies have them in development. There's multiple variants, memristors, resistive RAMs, phase change and so forth. And fundamentally what they present is a different price-performance trade-off. The potential for density growth is much greater. The potential for, if they're mostly persistent, they are almost uniformly slower than DRAM, and in different ways. So what they do is that they create an opportunity to have a different hierarchy of memory, where you have some DRAM, you have various kinds of fast memories, and then you have this, and then you have flash, and so forth. It has a lot of potential for, actually it's being primarily attacked at the data center, but it also has a lot of potential for edges and so forth, because it can change the power price latency dynamic. Software, it's a challenge for software to deploy, and software is struggling to deploy it. There's a potential for machine learning types of software, primarily because of the structure of the computation, and I think it's easier there than it would be for other, more arbitrary pieces of software.
Okay. So with that, I would like to open up to the audience for any questions. Yep, please.
Hi, I'm Surya, I'm the founder of Sirap Technologies. We are a startup developing automated driving technology. We talked about hardware. I do not know about eating up the world, but one thing that we know is hardware does very well is moving data around. But we are interested in understanding when would hardware be able to resolve congestion on 101 or 280 at peak times, because ultimately, it's about moving vehicles, so I believe hardware can do the job, but we're interested in knowing what your opinion and what your thought is about it.
Anyone take it?
Sure. I mean, we are
Clearly,
seeing
software
significant.
hasn't solved that problem yet.
Yeah. Yes. So I think on the autonomous side, there is a lot of progress being developed. And once you have autonomous vehicles, hopefully the congestion problem will be much simpler, because your efficiency of the utilization of the roads will increase significantly. As you really have, there is no slow-moving traffic or a fast-moving traffic and various speeds. I think it will be all managed. So the path to solving the congestion, I think, is an autonomous vehicles moving in that direction. And we see, at least in the next 3 to 5 years, there will be significant advances will be made in the autonomous vehicle space. So.
Sure, sounds good. And we are working on that, definitely. All right, anybody else?
Yeah, this is Puneet. Nisha, I have a question for you, especially because you have software background and storage background. If you think about the memory, the DRAM, and the flash memory coming in and SSD, the way I understand, and I'm actually from business side, so I can probably oversimplify it. It looks like the software and the intelligence and the firmware and the controller really makes a difference to the storage world, because otherwise you are more like a volume player or manufacturing or a process player. So what we are saying is basically software is making a difference, and that's where companies want to move and make a differentiated position in the market. How do you explain that dichotomy where in that world we kind of talk about software making a difference, whereas here the discussion has been more about hardware mapping? Maybe both are important, but I just wanted to get a view, because you probably have a different profile having worked on software side and now on this panel in the hardware.
Sure. So I've spent a fair amount of my career at the software-hardware boundary, with hardware companies, understanding how that hardware can be used to help people who are trying to solve their problems with software. So if you look at kind of these things that, like Flash and so forth, fundamentally, Flash is a hardware innovation that requires firmware, and depending on whether you call firmware software or hardware, it depends on who you ask, requires firmware to kind of make it fully usable. And I think it follows a similar pattern to what he has been talking about regarding learning how to do it first with software. and then pushing it down. Because one of the things that we learned, particularly building, Flash translation layers, is that at the beginning, all Flash translation layers were written entirely in software because nobody really knew how to do them and how they would work with different workloads and things like that. And after a while, patterns emerged, and you started to learn what good behavior looked like. And at the same time, software wasn't running fast enough to do these things in software. So good behavior became encoded in hardware, and things happen much faster. So that's a natural kind of evolution of things. So it's not really a hardware or a software. It's kind of the combination of both.
Hi, this is Nimit from IT Madras. I have a question in general about startups in this space, startups making chips for AI, ML. So hardware is really unforgiving, and what do you guys think about startups? How it's really hard to do a startup in this space. Like, how does a startup compete against NVIDIA or Intel in this space, given you can't raise as much capital, and if your chip fails, that's it. It's like building a rocket. If it fails, you go out of business.
So I have, maybe, I want to take that question. I have actually, because I've spent a fair amount of time in the investment side in my career. Given what's happening in ML, if you look at it, the landscape today, there are a number of startups that are actually going after the data center space, starting with GraphCore, Cerebras, Wave Computing, now SambaNova. And then, of course, there are many, many startups on the other side for the edge, starting from, I'm going to say a few names, DeFi, Mythic, there are people like Horizon Robotics building their own chip, et cetera, et cetera. There are like 50, 60 startups. I think from where I see is for a startup to be able to go after the ML market, maybe there is more opportunity on the edge side, because it's really going after NVIDIA and Intel, and now to go against TPU in some sense, that's really who you're up against in the data center market. And it is a long and hard drawn battle, and time and money, and eventually, even Alibaba I was told they're building their own Ali NPU. So Facebook might build their own. Who knows what Microsoft will do. But on the other side, there are more opportunities because you can go probably for specific applications. You may not need to raise as much money. If you have some differentiation in technology that you can sort of capitalize on, the scale in terms of effort and money and time may be quite different. So that's just my observation.
Do you think it's better to focus on like more of a software solution first and demoing it on like FPGA and then doing more of a...
Right, so that's just, so it used to be in the past that people would build up a prototype using FPGAs, show demonstrations, go raise money. But nowadays, I think, what I'm seeing is people are able to go raise money and then do that as a part of their development process, while they're building the chips, et cetera.
Thank you.
Okay, Vipin, maybe one more question? Yeah. Okay, so one more question, I will wrap it up. Thank you, guys.
Hello all, I'm Fabrice from IIT Bombay. I believe Ashish mentioned that it's quite likely that general purpose CPUs, general purpose GPUs, and accelerators will coexist in the future. So I kind of wanted a clarification on the accelerator part of it. It feels like today the accelerator market is kind of immature. It's very fragmented. And we have application-specific accelerators, domain-specific accelerators, and everything in between. So which way do you see this market evolving and progressing in the future, and how long do you think this will take?
So I think you are asking how, in terms of SoCs, they would exist, or you are asking how the general edge. So I think edge, everyone will, as Debu was talking about in response to the previous question, I think there will be a lot of different kind of edge devices will be built with the different accelerators. What I was talking about is more how the architecture of SoC or architecture of edge any compute would look like. We'll have a CPU and a GPU and an accelerator component. It could be different. Now, what those accelerators are, they could all very well vary based on what applications you are doing. I mean, if you are camera processing, then accelerator for that is different versus if you are doing some humidity sensor, then accelerator for that is different versus you're looking at some voice stuff, the accelerator for that could be different. So I think that will vary, and which is why I think his answer about doing something innovative in the edge is much more relevant.
Right. If I may, a follow-up question. So do you believe that there is any scope for standardization in this whole procedure, or is this variance going to remain as is for a long, long time?
I don't know. Debu, you want to take
For everyone, actually.
Sure. So in some sense, this is early days in ML, and things are changing rapidly. I mean, if you go to sleep for a week or two and wake up, the world changes.
Yeah.
That's the kind of situation. So I think standardization only happens when things kind of start to settle down, and for a given type of application, you have come to a conclusion that you have a few best candidates for doing those, and then there would be maybe some, I'm giving the example of, say, communications. I mean, I was very familiar with it because I did it for 30 years. We used to go to standards committees. Companies will come up with proposals. But by and large, it will be, the difference is what coding scheme you're going to take, which specific modulation scheme you are going to take, what messages you're going to pass. So we have not reached that state here.
Right.
Yeah.
Thank you.
Okay, thank you. If we can take about 30 seconds and sort of summarize what you want the folks here to take away.
Yes, I think my summary is, it's hardware is not going to eat the world and software is not going to eat the world. I think it's all going to coexist, but the fundamental paradigm for how we design software and even hardware is going to change. I think it's going to become more driven by machine learning and the designs for machine learning algorithms, and how you are training your networks is going to be becoming more in that direction versus what used to be a general purpose CPU and all algorithms, software driven of the past is going to change that now to the future.
Okay, Nisha?
So I think there's a lot of change happening in both hardware and software, and sometimes together, and it is primarily being driven by the consolidation of apps, if you will. Even though there's a lot of different apps, some of the app structures, there are some large app structures that are, starting to really dominate, and machine learning is easily the biggest one of those, and I mean all the kinds. And within that, and combined with the fact that there's all these distributions. I mean, compute goes out, then it goes in, then it goes out again. Currently, we're on the out, where it's heading, towards the edge, and for a while it'll go that way before it goes back in. So in that sense, there's tremendous opportunity for new hardware and tremendous opportunity for new software.
All right. So I think, in some sense, I think, in ML, I mean, software. If you look at it from the perspective of the users, the software frameworks that have kind of getting established, and hardware is somehow kind of it's kind of used to be opposite before, but now it's kind of like hardware has to be able to run those frameworks, has to be able to run what people already are using. Mm-hmm. So in that sense, if you look at TensorFlow, if you look at TensorRT, if you look at things that have become popular and there's large ecosystems that's just getting established, whatever hardware you build, you kind of have to cater to that. So, but there is a lot of innovation to be done in hardware, but while it remains compatible to the established software framework. Software frameworks are not going to change for you to accommodate your hardware.
So looking at what you just said, the software frameworks are sort of becoming more standardized,
yes.
And that actually opens up a lot more diversity for hardware to be out there. So in that sense, I think in this particular domain, you will see a lot more of hardware coming out.
Yeah, to make things efficient.
Right, faster.
Faster, yep. More power efficient.
Exactly.
Form factor for different domains. Yep.
Okay, with that, we will conclude and like
Thank you very much. Thank you.
Thank you.
Thank you. You know, and one of the